All right, so good morning. This is March 28th, college algebra. A couple of announcements to make. WebAssign homework is due on April the 2nd. It was originally due April the 1st. I realized that was Easter, and so I put it off till the next day, so it's April the 2nd. That's 3-4 and 3-7. Remember that 3-4 is on composition of functions, and 3.7 is on inverse functions. And so those two sections are due April the 2nd. Remember, the reason why we talked about those two sections is because those are lead-ins to talking about exponential and inverse functions. So that's why we had to go back and cover those things. Exam 3, we're not even going to worry about Exam 3 right now because it's still a long ways away. But the window for that will open April the 19th, which is just 3 weeks from tomorrow. So you do have a while to be thinking about Exam 3. And right now I wouldn't think about Exam 3 at all. Exam 2, so the window on that finished up yesterday. I will, at the very latest, have your grades posted on your WebAssign gradebook by April the 2nd. Remember that I always send out a remind message to everybody when I've posted the grades. And also don't forget that you can get a graded copy of your exam back by just simply emailing me, and I will send you back an attachment with your graded exam. The W day for the class, just want to remind everybody of that, is April the 6th. So remember what a W day means is that's the last day during the semester where you can get a W in a class. So if you have any questions about your grade, talk to me about it. Send me an email, send me a WebAssign message, send me a remind message, whatever, and we can talk about your grade and what your status is if you're concerned about it. Online office hours, because of the exam, we kind of had a disruption in online office hours, but the regular online office hours will resume today. So don't forget that those are Tuesday, Wednesday, and Thursday from 11 to noon. And then on Tuesday and Sunday evenings from 8:30 to 9:30 p.m. And then occasionally I can make appointments outside of those hours. All right, and so today we will be covering exponential functions. And so graphing by plotting points, graphing using transformations, and some compound interest applications. That's our target for the day today, is to talk about exponential functions. All right, so first of all, remember that inverse functions, I just want to write a couple things down here that we need to remember here. So inverse functions are functions where you have f circle g of x, which is defined to be f of g of x is equal to x. And g circle f of x is equal to g of f of x is equal to x. This is sometimes called inverse cancellation. So in other words, the two functions in some ways kind of cancel each other out. So for example, in a very simple setting, the cube root function and the cube function are inverses of each other, right? Because when you take the cube root of something that's cubed, right? In other words, you're doing both things. You're taking a cube root and you're cubing. What happens? Those cancel each other out and you're left with x. It's like they undo each other, right? If you take something and add 2 and then subtract 2, right? What happens? You get x. Adding 2 and subtracting 2 are inverse processes. Those are inverse functions. Taking something and multiplying by 2 and then dividing by 2. Those are inverse functions. You're left with x. Right? Those are all examples of situations where you've got two operations, two functions that kind of cancel each other out. They undo each other. The reason why we needed to talk about those kinds of functions is because the exponential and logarithm functions have this property. Exponential and logarithm functions, so exponential and log functions have this property. They cancel each other out. So they are inverses of each other. And that's why we had to talk about inverses first before we talked about exponential and logarithm functions, right? So exponential and logarithm functions are two kinds of functions that have this property that when you apply them, it's like they cancel each other out. They undo each other. And remember that another way of saying that is that they switch or interchange x and y values. Right, that's an important way to look at it, is that they interchange or switch out x and y values. All right, so with all that in mind, then let's go ahead and start talking about exponential functions, right? And we will not talk at all about logarithms today. We will start talking about logarithms next Monday. All right, so exponential functions are functions that can be written like this, that the f of x is equal to b raised to the ax power. Right? That's a general form that we're going to use for exponential functions. It's a constant raised to a variable power. And so you might write it that way, that it's a constant raised to a variable power. And this is the first kind of function we've seen this semester where the variable is in the exponent. That's what makes a function exponential, is that the variable is in the exponent. And we have not seen a function where that has been true. And so this is our first kind of experience in college algebra, at least, with functions like that. All right, so that's what we want to do, is we first of all want to talk about some functions and some very basic things about graphs of those kinds of functions. So we start off with a very simple exponential function, just 2 raised to the x power. Right, notice it's a constant raised to a variable power, and the x is in the exponent. Right, it's a constant raised to a variable power. The x is in the exponent here. So if we just plotted points, literally made a little t-table, and I'm going to make the t-table horizontal right here, and we picked x values and calculated the y value from that, right? So, we could pick x equals 0, and when x is equal to 0, you get 2 to the 0 power, and remember 2 to the 0 power is equal to 1, right? Anything to the 0 power is equal to 1. Anything except 0. When x is 1, you get 2 to the first power, which is 2. When x is 2, you get 2 to the second power, which is 4. So this all appears to be easy enough. When x is 3, you get 2 to the third power, you get 8. Notice that the y values here are just doubling every time in this particular problem, or for this particular function. When x is 4, you get 2 to the fourth power, which is 16. Now, one thing I did not do here is I didn't pick any negative x values. So let's do that. If you pick x equals -1, so then you get 2 to the -1. But remember what a negative exponent it does to a fraction, or to a constant like that. If you have a negative exponent, so if I have x raised to the -a power, remember that's 1 over x to the positive a. Then a negative exponent takes a number and it essentially turns it into a fraction. It flips it, right? It looks at the reciprocal of that. And the same thing if you have a fraction raised to a negative exponent, it simply inverts the fraction, and then the exponent becomes positive, like that. So 2 to the -1 here.
How come it's different? Sorry. How come it's different to if you're just raising it to a normal power? Because if you raise it to a normal negative power, it becomes positive. So why are we now making it into a fraction?
I don't think I understand your question, because that's...
So if it was like x to the power of -2,
yeah,
wouldn't it become a positive?
Well, it would be 1 over x to the +2, like that. Right, that's the rule for negative exponents. If you have x to the -5, that's 1 over x to the +5. right? It takes.
So why don't we do that when we do constants to the powers?
We did. That's so 2 to the negative 1. That's exactly what I did. So that's 1 over 2 to the positive 1, right?
Okay.
2 to the negative 2 is 1 over 2 to the positive 2. Right, so we're doing exactly the same thing. We're taking the base and we're just moving it to the denominator and changing the exponent to a positive. Do you see, Anne-Marie, are you okay with that? Does that make sense?
Yeah, I just never write it as the fraction, so.
Yeah, it's always going to be a fraction like that. So the negative exponent takes the base, moves it to the denominator. And so it's like for negative 1, you get 1/2. For negative 2, like I showed you at the bottom there, that's 1 over 2 squared, so that's 1 over 4. Negative 3 is going to give you 2 to the negative 3, which would be 1 over 8. Right? It takes the 2, moves it to the denominator, and you change the exponent to a positive, and then you just multiply it out like that. All right, so let's see what the graph ends up looking like. And Anne-Marie, if that doesn't make sense, you stop me and we'll talk about it some more, okay?
Yeah, because I would have just done like 2 to the power of negative 2. I would have just squared it and got 4, not 1.
No, see, because look, the 2 to the negative 2 and 2 to the positive 2 can't be equal to the same thing. Right, 2 to the positive 2 is 4.
If you squared a negative, you get a positive.
But the base is not the negative there; it's the exponent.
Oh, okay.
So,
yeah, that's what I'm getting.
So that's a difference between. Yeah, don't confuse those two things. Right, this is 1 over 4 here. This is positive 4. I agree with that. But yeah, I think that's what you were doing. You were confusing a negative base with a negative exponent.
Yeah, I was getting them mixed up.
Okay. All right, so let's see. What do you get here? You get 0, 1, 1, 2, 2, 4, 3, 8. 4, 16 is probably too high to find it there. Negative 1, 1/2, negative 1, 1/4, like that. Negative 2, 1/4, negative 3, 1/8 is really getting hard to even picture right there. It's really close to the x-axis. And you get a graph that looks like this. And notice that the graph starts to rise really fast. And in fact, the graph rises faster than any other function that we've seen this semester. These are very fast rising functions. This is sometimes, by the way, this shape right here that I've got is sometimes called a growth curve. It's given a name, and this is called a growth curve. One reason why it's called a growth curve is because it kind of simulates population growth. If you take, for example, a single-celled organism and how a single-celled organism multiplies, right? There's first one cell, and then that one cell subdivides into 2 cells. Those 2 cells each subdivide, so now you have 4. Those 4 cells subdivide, now you have 8, right? So it's kind of modeling that kind of population growth. And it also describes how money grows. These are things that grow exponentially. Populations, diseases, like I said, money, radioactive decay. Those are all things that either grow or decay exponentially. In this case, it's called a growth curve. A couple of things to talk about with this graph. Notice it's always increasing. That's right? So it's always a rising graph, always increasing. It's never a decreasing graph. Also notice that the domain here is all reals. If you just look at the graph, right, there's no breaks or tears in this graph, and so the domain is all real numbers. And then the range, a couple of things I want you to note here about the graph. Notice that it has a horizontal asymptote at y equals 0. In other words, the x-axis is a horizontal asymptote for this graph. The graph gets close to this asymptote, right? It gets close to the x-axis, but never ever gets to the x-axis. It never crosses it at all. So the graph gets closer and closer to 0 there. So there's a horizontal asymptote. And so the range on this graph is from 0 to infinity, and there's parentheses around the 0 because it never actually gets to 0. All right. I'll just also notice that you not only does it go through the point 0, 1, but it also goes through this point right here, 1, 2. And notice that the y coordinate happens to be the base here. So when x is 1, the y coordinate is the base that we were talking about. The base in this problem is 2. Right? That's going to carry over to other exponential functions that are in this form like this. All right, so let's look. We're going to walk through a couple of examples of problems where we're plotting points. Okay, so the next one I want to look at is let's look at f of x equals 5 to the x. So similar kind of function, but the base is different. So this one should be a little bit easier to go through now that we've done 2 to the x. So notice that when x is 0, you can still get 1, right? And so any function, you know, that's in this form, f of x equals b raised to the x power, what's going to happen here is that when x is 0, y is always going to be 1. And then when x is 1, what do you get here? You get 5. And in general, if you have b to the x, what happens when x is 1? You're going to get the base. You're going to get b. And I'm going to actually write the word base, but I'm going to also write equals b right there. So functions in the form b to the x always go through 0, 1, and they always go through 1 and whatever the base happens to be. When x is 2, you're already up at 25, and when x is 3, you're up at 125. This is an incredibly fast rising graph. And then when x is negative 1, you get 5 to the negative 1, which is 1/5. When x is negative 2, you get 5 to the negative 2, which is 1/25. The graph gets close to 0 really fast. And so here's our graph. So notice this graph goes through 0, 1, and it goes through 1 and what the base is. 1, 2, 3, 4, 5 right here. Right? And a very fast rising graph. And if you know it's a growth curve, and it also goes through negative 1, 1/5, like right way down here. If you know it's a growth curve, just those 2 points right there give you a pretty good sense of what the graph looks like. Very fast rising graph, and those faster rising than 2 to the x. I think it's helpful to put 2 to the x on the same coordinate system here. 2 to the x goes through these points like this, and 2 to the x is the same basic shape, but notice it's a slower rising exponential graph. So 2 to the x is down like that. And so obviously 3 to the x, you know, if you were going to continue this process here, 3 to the x, what would you expect about 3 to the x? Well, 3 to the x ought to rise faster than 2 to the x, but not as fast as 5 to the x, right? So if you have 3 to the x, again, you get 0, 1, and you get 1, 3, and you get 2, 9, and you get negative 1, 1/3, right? And so 3 to the x is kind of in between these two graphs. So 3 to the x goes through 1, 3, and it goes through 0, 1 like this, and kind of hard to draw in that region, but 3 to the x is kind of looking like this. Right, so notice that the bigger the base, the faster the rise in the graph for the exponential function. And the smaller the base, you know, so like we could use f of x equals 4/3 to the x, let's say. So 4/3 is a number a little bit bigger than 1. Even at 4/3, let's see, so you're going to get a growth curve here. Let's plot some points here. So when x is 0, you still get 1. When x is 1, you get 4/3. It's the base. Notice it doesn't matter that it's a fraction. That's okay. And when x is negative 1, you get 3/4. Right? It flips it. Remember that a negative exponent flips the base like that. So 4/3 to the x kind of looks like this. It goes through 0, 1, but it goes through 1 4/3, which is like right in here. And so this is a growth curve also, but it's a slower rising growth curve, right? Same basic shape, and it'll continue to rise faster and faster, but it's just slower than the others. So there's 4/3 to the x2, the x3 to the x5 to the x. You can see they all go through 0, 1, and they all go through the base when x is 1, right? When x is 1 right here, when x is 1, the y value you get is going to be whatever the base is. So if you look at all these points right in here, the y value is whatever the base happened to be for that exponential graph, like that. They all have horizontal asymptotes on the x-axis. Their domains are all reals, right? They all have that horizontal asymptote, like I said. So very similar shapes. It's just how fast the rise is in the graph is controlled by whatever the base is. Now notice all the bases I've written so far are all bigger than 1. You never talk about a base being equal to 1. So let me back up here real quick and talk about that restriction here, is that the base is never equal to 1. That the domain for these kinds of functions is always all reals. The range is from 0 to infinity, and there is a horizontal asymptote on the x-axis for these kinds of functions, right? That's kind of a characteristic for all of these kinds of functions here. But, oh, and by the way, one other thing, let me back up one more time here. The base not only is not equal to 1, but the base must be positive. Right? Base can never be negative. We never talk about negative bases for exponential functions. All right, so with all those things in mind then, let's look at a base that is that's smaller than 1, like 2/3. Let's look at this function and see what the graph looks like here. F of x equals 2/3 to the x. So, when x is 0, you get 1, like always. When x is 1, you get 2/3 to the 1, which is 2/3. And notice you get the base. You get 2/3. When x is 2, you get 2/3 squared, which is 4/9, which is actually a little bit less than a half. When x is -1, remember what a negative exponent does to a fraction is it inverts it. So this is 3/2. So if you look at this particular exponential graph, there is going to be a major difference between this one and the ones we've been talking about. Because the base was less than 1 here, notice this graph goes through 0, 1, goes through 1 2/3, and notice 1 2/3 is actually lower than 0, 1. And then it goes through -1 3/2, like this. And so you get a graph that is a similar kind of shape, except this is a falling graph as opposed to a rising graph. Everything else is kind of the same, but this graph is a falling graph. This is sometimes called a decay curve. And so it's a decreasing graph, right? It's a decay curve. So when you have f of x equals b to the x, and b is greater than 1, you get a growth curve. If you have f of x equals b to the x, but b is less than 1, you get a decay curve. Remember that b has to be positive no matter what. So I didn't put that in there, but b has always got to be a positive number. So if the base is bigger than 1, you get a growth curve. If the base is less than 1, you get a decay curve for a function that's in this kind of basic form right here. All right, now what we want to do here is we want to talk about a little bit about using function transformations to sketch transformations of these kinds of functions. Now, what we're going to do first, though, is we're going to look at a very important exponential function. There's one exponential function that's more important than any of the other functions we have, and I want to talk about that function. And so to first do that, I want to put the graph of 2 to the x and 3 to the x on this coordinate system again. So here's 2 to the x, goes through 0, 1, and 1, 2, and it's a growth curve, right? So here's 2 to the x, and then 3 to the x goes through 0, 1, and 1, 3. It looks like that. All right, there's 2 to the x and there's 3 to the x. There is one exponential function that is more important than any other exponential function. It's sometimes called the natural exponential function. And the base for this exponential function is, believe it or not, is an irrational number. In other words, its decimal goes on forever and never repeats, it never ends. It's crazy. You have these nice exponential functions like 2 to the x and 3 to the x, where the base is a really nice number. 2, 3, very simple whole numbers. But the most important exponential function, the one that occurs most often in applications, is one where the base is not even a number you can write as a fraction, where its decimal just goes on forever. So we use an abbreviation for this kind of this function, the natural exponential function. It's called f of x equals e to the x. And e is an irrational number, and e is approximately 2.71828. But that decimal actually repeats forever, or doesn't repeat, it goes on forever. It never repeats. So it's this crazy number that's between 2 and 3, approximately 2.7, and that is the most important exponential function we have. So if you look at plotting points on this function, right, when x is 0, you still get 1 because that's e to the 0. And let me put that in here, that's e to the 0, but that's 1. When x is 1, what do you get? You get e to the first, which is approximately equal to 2.718, right? And so on. You could substitute positive 2, -1, all those kinds of values in there. And your calculator you could actually use to get these values. Now, on a calculator, what you have to do, like if you wanted to find e to the second power, you have on a TI-84 or an 83, you actually have the ln key on the far left column. So this is the far left column. Like that, and then right above that is a e to the x, like that. It's not its own key, it's above the ln key. And so what do you have to do to get e to the x? You have to hit second ln. So you enter the second key first, hit that one first, that's the yellow key on a TI-83 or 84, and then you hit the ln key. And when you take those two keys and hit them in sequence like that, this is what you're going to come up with on your screen. It'll be e raised to a power, and then you'll actually be able to put a power in there like that. So to enter e to the second power, you hit second, and then ln, and then you hit the exponent, 2. And then you should also hit the right parenthesis to close off the parentheses. The left parenthesis comes up automatically, and so you have to put in the right parenthesis to kind of close it off like that. And when you get that, when you do that, you get that e squared is approximately equal to 7.389. All right, so that, and so you can enter any exponent in there that you want if you needed to get more y values here. We don't really need these y values because we know that this is a growth curve. And so we know that e to the x goes through 0, 1, and goes through 1e, which is about 2.7. And what do we have here? Notice is that e to the x is a function that rises faster than 2 to the x, but slower than 3 to the x, right? It's kind of in between 2 to the x and 3 to the x. For our purposes, what I want you to know is I want you to know and be able to replicate this graph. You need to know what the graph of e to the x looks like, and you need to be able to make a rough sketch of e to the x pretty relatively quickly, right? That it goes through 0, 1, and it also goes through 1e. And notice where I put that second dot is between 2 and 3. It's closer to 3 than it is to 2 because it's about 2.7. Right? And there's our graph for e to the x like that. All right, and so I want you to know that graph. That's kind of like a basic graph. And so then that should allow you to sketch things like this. E to the x minus 3, like that. If you subtract 3 from the e to the x, notice that would be a shift. Using what we know about transformations, this would be a shift down 3 units. Right? So here's e to the x. Right, e to the x goes through 0, 1, and 1e, right about in there. Right, it's this growth curve, and I'm going to make this a dashed graph right here, because that's not our final graph. And then what is it? It's that graph shifted down 3 units. Now what I would do here is I would definitely sketch in this asymptote, because the asymptote is going to shift down 3 units. That asymptote is on the x-axis, so it shifts down 3, and then we get our graph sitting above that asymptote. And all we're doing is taking every point and literally counting down 3 units. And so here's e to the x minus 3. So here's e to the x. Here's e to the x minus 3, like that. It's a shift down 3 units. Right? Notice that the domain for that function is still all reals. That hasn't changed at all. But the range has changed. The range is now going to be from negative 3 to infinity. All right? The range is, because the horizontal asymptote is shifted down 3 units. All right, if you have f of x equals e to the x plus 2, so e to the x plus 2 would be a shift up 2 units. And so, once again, here's my graph. Didn't need the x-axis to be quite that big, but that's fine. I'm going to go ahead and put e to the x on there again. So here's e to the x, goes through 0, 1, and 1e. Remember, 1e is about 2.7 for the y value there. And it's a growth curve. So there's e to the x, like that. But then e to the x plus 2 would be that graph shifted up 2 units. So what happens? The horizontal asymptote shifts up 2 units. The horizontal asymptote here is going to be at y equals 2. Just like on this one, it was at y equals negative 3. And then we get the shifted graph. Just every point shifts up 2 units. And here's e to the x plus 2, like that. All right, so those are shifts up and down for e to the x. So e to the x is like our basic graph at the very top of the screen here. This would be our basic function, and then the other functions below that are transformations of that basic function. All right, so definitely want you to be able to do transformations. So let's look at some more transformations. So let's look at f of x equals e to the x plus 4, like that. Now, don't confuse that, but be really careful. Don't confuse this. So let's see, don't confuse with f of x equals e to the x plus 4, right? That second function, that's the one we were just talking about on the last screen. And what am I doing? I'm adding 4 to e to the x. So this is a shift up 4 units. But that's not what I'm doing on the function that we're looking at in our problem here. This one, I'm adding 4 to the x value. And so this one is a shift. Don't forget what happens here. This is a shift to the left 4 units. Remember, when you add to the x value, you're shifting to the left, and when you subtract from the x value, you're shifting to the right. So this is a shift left 4 units. So notice this function has no change in its horizontal asymptote. So here's e to the x. I think it's never a bad idea to put this basic graph up first. So e to the x is our growth curve that goes through 0, 1, and 1e. Right, so there's e to the x. It has a horizontal asymptote on the x-axis. And that horizontal asymptote stays put because this is simply a shift to the left 4 units. So you're just simply counting backwards 4 units. 1, 2, 3, 4, like that. And here is our new graph. Back 4 units to the left. Still a growth curve. Right, just shifted backwards. And so here's e to the x plus 4 right here. Right, that's a shift back to the left 4 units. All right, f of x equals e to the x minus 5 minus 4. All right, so that function has got the x minus 5 shifts the graph left. I'm sorry, whoa. The x minus 5 shifts the graph right. That's better. 5 units. And the minus 4 shifts the graph down 4 units. All right, so I would go ahead and put in my basic graph right here. Definitely would do that. So here's my basic graph. Goes through 0, 1, and 1e. Those 2 critical points right there. There's e to the x. And so this one shifts to the right 5 units and down 4 units. And now since it shifts down 4, the horizontal asymptote is shifting down 4 units. I would always, if there's a shift up or down, I would put in the horizontal asymptote and actually sketch it in. So here are horizontal asymptotes at y equals negative 4. And this graph is shifted to the right 5 units. You could even put in the shift to the right just kind of as a dashed y-axis like that. Not a bad idea because it kind of helps you keep your perspective on things. And so our graph is going to be sitting down here. It goes through 0, 1, and 1e, and those points are going to shift to those 2 spots right there. And here's my new graph. Like this. So this is e to the x minus 5 minus 4, like that. Right, so notice it, again, it's a shift to the right. Five, and it's down 4. Like so. All right, so a little bit more with transformations. Let's look at some reflections and how those work. So don't forget that when you stick a negative sign in front of a function, that's a reflection around, so it's a reflect, and this is around the x-axis. And when you stick a negative sign in front of the x value, you reflect, but this is around the y-axis. We've talked about that way back when we did transformations about probably a month, 5 weeks ago, something like that. So for our problem, we want to look at f of x equals the negative of e to the x. Right? And so that would be the graph of e to the x, but reflected around the x-axis. So I would put in my graph for e to the x. And I think, we've sketched it numerous times now in the last 20 minutes. So you should be getting the idea here. It goes through 0, 1, and 1e. right? 1 in E, remember, is approximately equal to 2.718. And you can't get 2.718. You can't do it accurate enough, but about 2.7, you ought to be able to get pretty accurate, relatively accurate on that. So a little bit closer to 2 than to 3. And here's our graph. So there's e to the x. And then the negative of e to the x is simply that graph flipped upside down, essentially. It's reflected around the x-axis. So those points, those key points, reflect around the x-axis. And here's my new graph. Right, and so this is negative e to the x right here. Notice this is no longer a growth curve. It's a reflection of a growth curve. Right, so it literally flips around the x-axis. All right, and then we have f of x equals e to the negative x. If you stick a negative sign in front of the x, not in front of the function, but in front of the x, now you're changing the sign of the x values, changing the sign of the x values, and this is a reflection around the y-axis. So here's our e to the x graph. I'm purposely sketching it every time we do this so you can start getting used to that being a very common shape for you to know coming out of college algebra. And so here's e to the x. So e to the negative x literally takes all these points and looks at their mirror images around the y-axis. So that point there at 1e flips over to negative 1e, changes the sign of the x value. And so now here is your graph. Right, and notice this is a reflection around the y-axis, and so this is e to the negative x. All the x values change sign there. Notice this growth curve actually reflects over and is now a decay curve. So e to the negative x actually is a decay curve, whereas e to the x is a growth curve. So this is growth right here. And when you reflect it like this, you get a decay curve, like this. All right, so I would want you to be able to go through and sketch some function transformations like this. I think this is important for you to be able to do. The only ones I'm going to look at are reflections or transformations of e to the x. Okay, so on a test, whoops, I have some homework here that I need to, we're going to talk about, but not quite yet. So on an exam, I might ask like this. I might say, use transformations of f of x equals e to the x to graph f of x equals the negative of e to the x plus 5 plus 6, let's say, like that. This would be as hard as it would get to. So what do you got going on here? The x plus 5 shifts the graph left 5. Negative e to the x plus 5 reflects x-axis. In other words, flips the graph upside down. And finally, negative e to the x plus 5 plus 6 is up 6. So a lot of different things going on in the graph. All right, but we can handle this. Just walk it through step by step. That's the important thing here, is just to walk this through step by step. So here's e to the x, like so. And then you take that graph e to the x and you shift it backwards 5 units. 1, 2, 3, 4, 5. So I'm just going to count backwards 5 units. And so here are our 2 key points shifted back to the left 5 units. Right? So that would be e to the x plus 5. And then you take that graph and you reflect it around. So here's e to the x, by the way. Here's e to the x plus 5 right here. Now you take that graph and you reflect it around the x-axis. So you're literally flipping it upside down around the x-axis. This is still not my final graph, so this is also dashed. And so this is the negative of e to the x plus 5. And then finally you take that graph and you shift it up 6 units. So I would definitely sketch in the horizontal asymptote. 1, 2, 3, 4, 5, 6 right here is the horizontal asymptote. Notice this graph is underneath that horizontal asymptote, but it gives you a good frame of reference to sketch our graph here. And so here's our graph finally shifted up. And it looks like that. All right, so this is negative e to the x plus 5, finally plus 6, like that. Right, and that's our final graph. Now, it's a little bit tricky, but if you just walk through it step by step, this should not be too bad to get through this kind of problem. All right, so now the next thing I want to do, so we've talked about graphing by plotting points, graphing exponential functions by plotting points. We've talked about the difference between a growth curve and a decay curve. We've talked about e to the x. We've talked about the idea that e is approximately equal to 2.718. And so e to the x has this basic graph that we've been talking about for the last 10 or 15 minutes. Now we've looked at transformations of f of x equals e to the x. So what we're going to do now is we're going to finish, pretty much finish the day here with looking at some applications of exponential functions. And the application we're going to look at right now is called compound interest. So compound interest is the idea of earning interest on interest, or having to pay back interest on interest also. So earning interest on interest, basically. So in other words, it basically goes like this, that if you were earning a simple uh, 4% on $100, then in 1 year, you have $104, right? Because what happens at the end of the year, they pay you 4% of $100 as interest, so you get $4 of interest, and you get $104. But now, if you have 4% compounded quarterly on $100, first of all, what they do is they pay you 1% each quarter. Not 4% each quarter, but 1% each quarter. So compounded quarterly means 4 times per year. Interest is compounded 4 times per year. So in other words, quarterly. And what they do is they take the interest rate, they divide it by the number of times you're compounding. So 4 times a year, 4% divided by 4 is 1%. So they pay 1% each quarter. So at the end of 1 quarter, they give you 1% of $101, and so that, or of $100, so that's $1. So at the end of 1 quarter, you have $101. But at the end of the second quarter, and this is where the compounding starts to come into play, now they're paying you 1% on $101. Right? And so they're not paying 1% on the original principal of $100. They're now paying it on the original principal plus the interest that you've already earned, which was that $1. Now it's only $1.01, and so now you have $102.01, right? And so this continues on. Third quarter, now you get 1% paid on $102.01, which is about $1.02. So now you have $103.03. And then at the fourth quarter, at the end of the fourth quarter, they're now paying 1%, not on the original $100, but now on the $103.03. And so that's $1.03. And so now you have $104.06. So notice there is a difference. Now, for $100 in 1 year, the difference is not that great, right? So simple interest just gives you $104. Compounding it quarterly gives you $104.06. But over a long period of time, over 20 years, 30 years, so for example, if you're talking about a house mortgage, or if you're talking about a car loan that maybe it's paid over 5 or 6 or 7 years, but it's a fairly large number, then it starts to become substantial. And so paying money back or earning interest, either way, this compounding feature can either work really, really in your favor over the long term, or it can work really, really against you in the long term, depending on whether you're trying to save money or you're paying money back. All right, so what we are going to do, though, is we're going to look at, we're not going to go through the nuts and bolts like that. We're going to actually look at some formulas here. So we have compound interest formulas. And just so you know, by the way, the weather locally for me is there's a storm not far away. So if all of a sudden I cut out, that's because I've lost power, and so lecture's over if I've lost power. So I'm going to try to get through these compound interest formulas here. There's two compound interest formulas. One is P times 1 plus R over N raised to the NT. And this is when the interest is compounded a finite number of times a year. So interest compounded a finite number of times per year. But there is another compound interest formula, and it's A equals P. Clean it up a little bit. A equals P times E raised to the RT power. And this is when interest is compounded continuously, or in an infinite number of times per year. Now that sounds crazy, and it really isn't as great a deal as it may sound, but interest is compounded an infinite number of times per year. And when this happens, this is called continuous compound interest. So when you see those words, continuous compounding, you're talking about using this formula. All right, so let's look at an example or two here to finish this up. So let's say I'm investing $1,000. Invest $1,000 in an account that is paying 3% compounded monthly, we'll say. And the question would be, how much do I have after 10 years? All right. So in our problem then, A is the unknown. A is the amount we have after so many years, and so that's what I'm trying to find. P is the amount of money I've invested, and so that would be 1,000. R is the interest rate. You always write this as a decimal, and so that would be 0.03. N is the number of compoundings per year. And so that would be monthly in this case. And so that would be 12, since it's compounded 12 times in a year. And then T is the time in years, and so that would be 10 years. So you plug those numbers in. You get A equals 1,000 times 1 plus the interest rate, which is 0.03, divided by 12, raised to the nt power, so that'd be 12 times 10 power. It's an exponential expression, and you can actually, then you just do the arithmetic to make the calculation. So let's see, so 0.03 divided by 12 is 0.0025. So you have 1,000 times 1 plus 0.0025, and this would be to the 120th power. So you have A is 1,000 times 1.0025 raised to the 120th power. On your calculator, you take 1.0025 and you'd put the caret symbol and then raise it to the 120th power. And so I get approximately 1.34935 power. You multiply that by 1,000, and you get $1,349.35 approximately. And that's how much we would have after 10 years in an account like that. All right, so now if we do the same problem, but we take and we invest $1,000 in an account that's 3% compounded continuously. How much after 10 years? Then now we use our continuous compound interest formula. A equals P times E to the RT power. So it's a different formula. So it's A equals 1,000 times E, that's our number E, 2.718 approximately. We don't ever enter 2.718 because we can use our calculator for this. The interest rate is 0.03, and that would be times 10. So this would be 1,000 times e to the 0.3 power, because that would be just 10 times 0.03, which is 0.3. On your calculator, you would enter second ln. Remember, we talked about that a little while ago. And then 0.3, and then finally the right parenthesis to close off the parentheses there. So when I do that, second ln, 0.3, close the parentheses, I get this value. I get A equals 1,000 times 1.34986. I'm rounding that last decimal place there. And times 1,000, this would be $1,349.86. And so that's how much I would have after 10 years in this interest, in this problem. And notice that compares to $1,349.35. So it's a total of like, what, 51 cents difference here after 10 years. So not a lot of difference overall. All right, so now as far as homework goes, you do not have WebAssign homework on compounded or on exponential functions at all. But instead, what I've done, so let's see, homework on exponential functions. I am not going to pick this up, but the homework is part of these notes, and it's the next 3 pages. The next 3 pages. And so let me show you what I'm talking about. So I've actually got the last 3 pages of these notes. I've got a couple of problems where you're plotting graphs by plotting points, plotting exponential functions by plotting points. And then a compound interest problem at the bottom, a continuous compound interest problem at the top, and then some transformations of e to the x. So you graph e to the x, and then you graph some transformations of e to the x. All right? All the things we've talked about in class today. So that's your homework. That's the problems I want you to work on in practice for exponential functions. So next time we'll be talking about logarithms. That's our next goal. So next week we are talking about logarithms. And so if you've not talked about logarithms before in your math careers, next week will be a big week because this will be something completely and totally new. And so it's very important that you either attend these lectures live or watch these recorded videos next week, especially as we introduce what logarithms are all about and how we use logarithms to solve problems. All right, does anybody have any questions at all?
I'm good. I do, but you might want to wait till we finish.